All right, in this video, we're going to be working BC Quiz 7.3, specifically the P and Q versions, where we are allowed to use Desmos. Really, for the first time I've ever allowed people to use Desmos on a quiz, but it's new age, we need to be able to use Desmos. So, didn't have a whole lot of success with it in class, but I still think these are good problems. I think my issues were more with how I administered and how much time I allowed for it, but we'll get there. So the number of bugs, is it increasing or decreasing at time t equals 60? And a of t is the rate the bugs arrive, and x is the rate at which they leave. This is not totally clear from the first two problems. I realized I had multiple windows of the same thing open. It's in number 3. They're dying at a rate of x of t bugs per day, so they're exiting the building. And then, but we'll need to use x of t on this number 1, and that's one of the reasons I didn't end up grading this quiz. But there were others. So if I'm interested in that, I'm going to have to consider which is bigger, the rate in or the rate out. So what I'm going to do is I'm just going to say a of 60 minus x of 60. That's what I'm planning on doing with the calculator. And then going over here to the calculator and actually copying in my functions. Now, what we discovered in class today was that, you're cool to type a of t. That's totally fine. A of t. This is going to take a while, but let's see. What was a of t? E to the sine of t to the 0.6. All right, so e to the power of sines and one of the nearby ones. Sine of t to the 0.6. So t to the 0.6. Can end that parenthesis and go over here. You don't want to name a function x of t. Desmos expects x to be an independent variable, and I'm not totally sure what the workaround is besides just call it f of t. So I'm going to call it f of t equaling, okay, that was the rate out, 2 to the power of 0.01t. Okay. Now, I will say I am not all that interested in, the graphs of these two things individually. I'll be more interested in maybe a different graph in the future, so I'm just going to turn those off and say, okay, I don't really need that. A of, it was 60, I think. A of, oops, 60 minus f of 60. And that's negative 1.059. So I'm going to go back to my paper, report my value, point out that that's less than 0. That's going to be a reason for my answer. And so I'll say the number of bugs is decreasing. Okay, how many bugs entered the building during the 100 days of summer break? Well, that would be the total amount of bugs in the building that entered, total in. So I'm going to integrate a of t. So I'm going to integrate from 0 to 100 a of t dt. And that's definitely a job for the calculator. So I will, you can type in int, or you can scroll down to calculus and ask for the integral from 0 up to 100 of a of t dt. That would give me 138.713 bugs. Oh goodness, I've already forgotten. Let me click around behind that and look really quick. I've got the answers. I should probably have those up anyway. 138.713. Okay, and if it does not say to round to the nearest whole bug, then we don't round. right? We only always three decimals. The only time we don't is when it explicitly says to not round to three decimals. And it doesn't say anything about rounding here, so we just go ahead and report the three decimals. And you've been in my area long enough, those who I was saying today in class, you've been in my area long enough, you know there's partial bugs down in that basement. So starting at time t equals 30, once all the bugs had eaten all the food, bugs began dying at a rate of x of t. Okay, assuming no bugs at time t equals 0, how many bugs were in the ground floor of the building when the teachers arrived for work at time t equals 100? Okay, so that would be just the number of bugs in there. So that would be 0 to 100 of rate in minus rate out. And notice that although I renamed x of t to f of t in Desmos, I'm still referring to x of t as x of t on my piece of paper, right? If I wrote f of t, the person who's reading it has no idea what I'm talking about because nobody ever defined f of t. And I don't think you want to go off to the side and be like, let f of t equal x of t for all t or whatever. That would be silly. So I go back to Desmos, and let's just go ahead and do a of t minus f of t. Oh, okay, but I think that'll be good. That this will give us an error here. It's like, we tap that, and it says integration must end with an integrand must end with an integration variable like dx. It's like I did end it with an integration variable like dx. I use dt. What you need to do is put parentheses around your integrand. Okay, and that actually makes a lot of sense because what it thought, actually where it was looking for you to put a dt or a dx was right there. Okay, and so that's kind of a different discussion on order of operations, but there you go. It's negative 5.556. Wait a minute. Yes, I just read right past that and made the error I hoped you wouldn't. Okay, so now I'm seeing why people got that answer sometimes today. Is because they weren't time delaying the f of t. Okay, so I'm going to go back to my paper and think about what I did wrong here. Okay, yes, definitely. I did not account for the fact that x started at t equals 30. So I'm going to need to only integrate a to get the total in, and then integrate from 30 to 100 rate out. That's much better. Okay, and that's going to be, I could just go ahead and use that 138.713, or I could just kind of go over here and adjust this minus the integral from 30 up to 100 of f of t dt. And then that's where we would get 27.790 bugs. Okay, now number 4 asks us for the value of a prime of 1. So we're definitely going to find that using the calculator. And then using correct units, interpret the meaning of the value in the context of the problem. Well, I can do that before the calculator. Represents the rate of change of whatever A means. So I'm going to go back up here and read bugs enter the ground floor of a school building at a rate of A of t. So the rate at which bugs enter the building okay, now I'm going to indicate my units of measure. A was measured in bugs per day, so it'd be bugs per day divided by the units of time, so that'd be per day at time t equals 1 day, right? We always need to have kind of the meaning. We need to be sure to include our units and be sure to include time as well, right? Okay, so that's 1 through 4. Oh, but I didn't actually find the value of a prime of 1. So go back over here and I just type in a prime, I can get that down there, of 1, and that'd get me 0.752. 0.752. There we go. All right, now this one will not require a calculator at all. Okay. G of x equals the integral from 2 to x of f of t dt, and we're looking at the picture of a graph of f. That means that we're going to need to be very clear about acknowledging that the derivative of g prime of x, is f of x. I'm going to just start with that. And then if we're interested in where g is decreasing, that's going to be where g prime is less than 0. And we know that g prime equals f, so I'm going to say that, okay, g prime, which I know is f, is a less than 0 function when x is between 1 and 6. I'm just going to leave it at that. That's my answer and my reason. And find all values of x where g has a point of inflection. Okay, so we're looking for a sign change in g's second derivative. Okay, g's second derivative is going to be f's first derivative. And so okay, so when does f go from increasing to decreasing? That's at -2 and +2. And the reason for my answer is the sign change of g double prime, which is f prime. All right, now we're going to find the limit as x approaches 2 of g of x over x squared minus 4. Okay, well, that's not what was, oh no, g is the integral of f. Oh, okay, yeah. So we would approach the integral from 2 to 2 of f of t. Okay, so, and, you know, expecting L'Hopital's rule, limit of a quotient, we're going to evaluate the limit of numerator and denominator separately. Limit as x approaches 2 of g of x is the integral from 2 to 2 of f, which is 0. And then the limit as x approaches 2 of x squared minus 4 is equal to 4 minus 4, which is also 0, right? We're never going to say equals 0 over 0 or even really mention 0 over 0 as a fraction at all, because we're interested in getting all of our points possible for the justification. Limit as x approaches 2, we're going to take the derivative of the top, g prime is f, divided by the derivative of the bottom is 2x. Okay, well, as x approaches 2, f is approaching -4. And 2 times 2 would be +4, so that's going to be -1. Now, finding the absolute minimum value of g on the closed interval -4 to 6. Okay, well, what I'm going to do is just go ahead and make my table. X and g of x, the closed interval -4 to 6, I'm definitely going to need to check my endpoints, and I'm also going to need to check any critical points. G prime of x equals f of x equals 0. When does f equal 0? That was x equals 1. Okay, now you might be looking at that and saying, well, that's a local maximum, so it can't be the absolute minimum, and that's true. Okay, but you would need to like totally justify that, and that's probably not something, you know, without specific training. If you want to train on that, come talk to me. I'll show you how to do it. But without specific training, you're probably not going to know how to do that. So, okay, over here, x equals 1. I'm going to do some geometry now. I'm going to need to find g of 1. Well, that's, oh, okay, I'm going to actually need to find that also. And g of -4 and g of 6. All right, so -4, 6, and 1. G is the integral from 2 to x, so let's do g of 6. Let's just integrate forwards. Do the easy one first. From 2 to 6, that's going to be the area of this triangle, which had a width of 4 and a height of 4. Okay, so half of 16 is 8. We're below the x-axis, so that would be -8. Okay, g of -4 equals the integral from 2 back to -4. Then go and, whoops. Okay, so I might actually, since this one's like geometry, I'm going to reverse the bounds and just make the integral negative. And you can do this however you want, but for me, I think that makes it easiest. Okay, so I'm going to cut it into this triangle right here, and then that has a width of 2 and a height of 6, so area 6. Okay, this is looking like 8 units of area. That's going to be 2 units of area. Okay, then over here, I'm going to have half of 4 would be 2, and then this is the same triangle that's down there to -2. All right, so that's going to equal the negative of 6 plus 4 and 8, that would be 18. Minus 2 is 16. Okay, so the negative of 16. And then g of 1 is going to equal the integral from 2 back to 1, which is the negative of the integral from 1 to 2. And all right, over here, I'm thinking, all right, integral from 1 to 2 is -2. The negative of that would be +2. Okay, so I'm going to go report that. -8, -16, and 2. Okay, I've computed my values. I have said why I'm interested in the x values. I've pretty much justified my answer. It might be best, you don't have that luxury if you're actually writing on a sheet of paper, but it might be best for me to bring my computations down here, drop them off, and say, okay, that's the work that led to my answer. And that's pretty much all you could say about this one. So there we go. All right, now I'm going to move on to Form Q, and the front side of Form Q is the same graph. We're going to start our integral at x equals 4, and we're going to integrate from 4 to x on f of t dt. And when we see one of these, want your first instinct to be like, oh, I need to figure out what the derivative is, write it down multiple times. Okay, the derivative of g is going to equal f. And if I'm asked about where is g concave down, I'm going to need to know where g double prime of x is negative. Okay, but g double prime, that's going to equal f prime. It's good to establish that. That's going to need to be less than 0. So when is f decreasing? Well, pretty much all the way down through here. And, x equals 0, you don't need to really worry about that. I would say that the graph of f is still concave down there because it's continuous and smooth. So, it would be hard to tell that the second derivative didn't exist at that point briefly, instantaneously, but then started existing again, and was pretty near what it was before. I don't think that would be perceptible if you were just looking at the graph of g. So I'm going to say g double prime, which is f prime, is less than 0. That's -2 to 2. Okay. And then find all values of x where g has a local maximum. Well, g would have a local maximum where its derivative, which we know is f, goes from positive to negative, and that would be at x equals 1. And you can see that in the graph. All right, now the limit as x approaches 4 if g of x over 3x minus 12. This is very similar to the one on Form P. That's going to equal the integral from 4 to 4 of g f of t dt, which is going to equal 0. I don't think you would need to write the integral there. This one's going to be L'Hopital's rule, expected to be L'Hopital's rule. When you see a limit of a quotient, right, evaluate the limit of numerator and denominator separately. Worst case scenario, you get numbers for both, and it's like, oh, well, it's just this over that. But if I do 3x minus 12, I'm going to get 4 times 3 is 12, minus 12, that's 0 again. Okay, so I need to use L'Hopital's rule. And I'm going to call this the limit as x approaches 4 of g prime, which we know is f, divided by 3. Okay, as x approaches 4, f is approaching -2. So I'd say this one's -2 over 3. Okay, now we're going to find the value of g of 2 and decide whether g is increasing, decreasing, or neither at x equals 2. All right, so g of 2 is going to be the integral from 4 to 2. And, because that one's backwards, I might. And this is just how I prefer to, integrate these with, you have to do the geometry, the areas. For me, thinking about the area formulas and also keeping track of what's positive and negative when I'm going backwards, that's just too much for me. I know a lot of the students in my class are perfectly fine with it. But yeah, you do this however you want. Because I think what's more important is that you understand what's happening with the derivative, or the increase-decrease behavior. So it was the integral from 4 back to 2. Okay, so the integral from 2 to 4, I need to figure out what this is. That way, you could look at it as a trapezoid. I'm just going to cut it up into manageable pieces. This is 4 units of area, and that would be 2 more. So the integral from 2 to 4 is -6. And so I have the negative of -6, and that is equal to 6. Okay. Now, is g increasing, decreasing, or neither at x equals 2? Yeah, you might be thinking, oh, well, it's increasing because as I went from where I started, 4, where it's 0, I went from 0 to 6 to, well, I'm still subtracting negative areas over there, as I'm going farther to the left. Then I should be increasing. And you are increasing as you move right to left. But remember, increase and decrease actually has to do with whether you're moving, when you're moving left to right on x. And also, what I was going to point out is that a valid strategy that I do think would help with this one is that this is the graph of g prime, regardless of where we start our integral. Right, you saw like how, on one form I started at x equals 4, the other one I started at x equals 2. It didn't really matter. Okay, it was f prime or g prime equals f regardless. So this is the picture of the graph of the derivative, and g prime of 2, which is f of 2, is -4. So that means that g is actively decreasing. Okay, so I'm going to say g prime of 2 equals f of 2, which is -4, which is a less than 0 number, and that means that g is decreasing. At x equals 2. All right, so for the backside, we've got bugs entering the ground floor of a school building at a rate of a of t, exiting at a rate of x of t. Zoom in on that, so in case you didn't have that information already copied down, you can get that. If we are going to use these functions, okay, I'm talking to you as if you have not already watched Form P. If you're going to be using these functions on more than one part, you need to just store them as is in Desmos. So we go over here and we add that in. Notice that I have not typed it in as x of t, because if I do, I'm not totally sure, I'm relatively new. Notice the graph is totally different. I think that might be the inverse function. I don't even really want to get into it. I feel like it might be x times t equals that, and then it's assuming, I don't even want to know. Just beware. X of t is not something that is going to go the way you expect on Desmos. And so, and that happens sometimes in AP Calculus, right? We need to use x of t because, we have position, velocity, acceleration graphs. One thing I was going to point out is that we can restrict the domain of one of these functions using that curly brace. So 0 less than or equal to t, which is less than or equal to 100. I'm pretty sure that's the restriction here. Let me go back and look real quick. Yeah, both for 0 to 100. I feel kind of regretful that I didn't do that on the other form, because had I restricted x of t to 30 to 100 like it was supposed to be, that one had kind of like an offset time where the bug started dying. If I'd done that, I kind of made an error, and it would have caught that error. It would have said undefined, because I would try to integrate a place where x of t really didn't exist. Okay, but, too late for that now. I just remembered that as I was typing in those functions. But, okay, if we're interested in how many bugs left the building between time 40 and time 70, we're going to integrate rate out. So that's from time 40 up to time 70 on x of t dt. I renamed it to f in Desmos, but I'm still going to call it x on my paper, because if I wrote f, nobody would know what I was talking about. Okay. On the other hand, here, if I'm going to integrate, which I can find in the calculus menu right there, from 40 up to 70 on f of, I feel like f and t should both be, one's on the quick menu off to the left, they've got extra room, but not maybe with time, and maybe a dt or a dx type command would be helpful. Okay, so 3.380. Is that really how many bugs exited the building? Okay, I guess we really don't have very many bugs exiting the building in this scenario. But, it doesn't seem to me like in my building the bugs exit very often, and I've already forgotten what the value was. Kind of not thinking that's what I got the last time I worked this problem. Let me make sure everything's okay. That is not what I got last time I worked it, but that's because I integrated the wrong function last time. I integrated a of t. Not sure why I would do that. Let's just change that on my answer key. Okay, is the rate of change in the number of bugs in the ground floor of the building increasing or decreasing? Is the rate of change increasing or decreasing? All right, so, I see on number 7, we're going to talk about the number of bugs, and then number 8, we're going to talk about number of bugs, so I should maybe define the number of bugs right now. I'm going to let n of t be the number of bugs in the basement, or the ground floor of the building. N is going to be however much we started with, which we started with 17, plus the total n, the integral from 0 to t of a of something, minus the total out, and because there's no offset in the time, I wouldn't have to worry about that. Oh wait, but dt, that's not going to be a good idea because t is how far I'm integrating. I've already used x. Let's pick a new letter like u or v or something like that. And then we'll say, all right, because really what I'm interested in is the rate of change is going to be n prime of t, which I could compute, throwing t in for the dummy variable. That would be a of t minus u of t, or minus x of t. And that's, then that's something we know that the net rate of change is rate in minus rate out. Okay, so we've got that, and if we're interested in if something is increasing or decreasing at time t equals 60, we're going to take its derivative. Okay, so we're going to do the derivative with respect to t at t equals 60 on n prime, because that's the rate of change, to determine if the rate of change is increasing or decreasing. So I'm going to go back. Okay, I've got it typed in. I've got n of t equals 17 plus the integral from 0 to t of a of u minus f of u du. And, oh, look, it's offering even to graph it in purple. And I don't really totally see that. Oh, yeah, because we're starting at 17. Okay, that makes a lot of sense. But I don't think I'm really needing to graph this. I think that's going to be tempting to y'all to use that on the absolute maximum problem, and that's the fast track to getting 0 points. Okay, really concerned about that. I don't want y'all doing that. On the real one especially. Remember, it's never going to be as easy as just graph it and be like, oh, I found the maximum, there it is. Okay, that especially now using Desmos, it's going to be a little bit more. It's going to be a little bit more involved than that. What we really want is n double prime of 60. Okay, taking the derivative of n of t, or n prime of t at t equals 60, negative 0.105. So I say it's decreasing. Now I will say I'm looking at my answer key on the digital key, and it says a prime of 60 minus x prime of 60 equals negative 0.105, which is less than 0, decreasing. So the work is largely the same. I just didn't think to already start in with n of t at that point. But if you just were talking about a prime minus x prime being a negative number, that's great. That's very similar. Okay, now at time t equals 0, okay, we already know there were 17 bugs on the ground floor. How many bugs were there when teachers arrived for work at time t equals 100? Okay, this is going to be very easy because I did all that legwork ahead of time. So that's going to be 17 plus the integral from 0 to 100 of a of t minus x of t dt. And, oh wait, no, not n of t. I actually want n of 100. Okay, that would not have been true. Okay, so now I need to go back over to my... Oh, and I see that there's an absolute maximum coming up, so I'm going to switch, and I'm going to evaluate this in a table. So I'm going to go over here. I don't think I'll be needing any of that. I will be needing n of t. But what I'm going to do first is, I'm going to call for a table, and you just type in table, or you can get it from that plus thing in the top left. You can kind of see that. I'm going to tell it, I actually don't want to just tell you what y is. I want you to tell me what y is. So I'm going to ask you for n of x1. That would be great. And we are, okay, we know at time 0 there is 17. Okay, that's not going to be useful to us. We're interested in at time t equals 100. That's 492.399 bugs. And again, nobody said anything about rounding to the nearest whole bug, so we don't round. Okay, we always report 3 decimals unless instructed explicitly otherwise, and there's no explicit instruction here, so why would we round? Okay, when the absolute maximum number of bugs are in the building, that would be, okay, we're going to have to do some candidates test analysis. We see that absolute maximum word, or we see that closed interval given to us. Okay, fortunately, I've already defined my function for number of bugs, so 0 and 100. I've already got those values ready to go. At time t equals 0, I had 17 bugs in the building. I just determined that we had 492.399 bugs at t equals 100. And now I need to know when does n prime of t, which I know is equal to a of t minus x of t, because I've written that down a couple of times, when is that equal to 0? I'm going to need to figure that out, and so I'm going to go over here and ask it to graph the derivative of n. You could say, a of t minus f of t, but I'm just going to say, where would that be? Y equals n prime, because that's really what I'm interested in. The derivative of the total is hitting 0. Okay, so that's graphing in black, and I'm interested in where this is equals 0. So I'm going to zoom out, kind of go, okay, that's interesting that the rate is very similar to the rate in. Oh yeah, because there's no bugs exiting the building between time t equals 30 and time t equals 70. Yeah, why would they? It's summer break. It's their time to shine. Okay, and so, but really this blue and red graph's kind of getting in my way, so I'm going to turn those off. Okay, this will allow me to zoom in and see what I'm supposed to see. Okay, so right there, I've got it. There's the 0. Hover over it, touch it if you're on a tablet, and then we're going to store that value. Okay, I'm going to get rid of the fact that it's a coordinate, because that's not all that interesting to me. I'm going to call this value... no, there's not a letter on the outside. I'm going to call it C. So C equals that. So 92.215.26. Okay, so that would be... I don't... 218.526. 2. Wow. That just goes to show you I need to have this on a split screen. Okay. Now with this one, I think because we're going to be pretty far off of 17 and 492, that was the only place where n prime equaled 0. I don't think it's going to really matter that we carry all the decimals, but it asked for the times, so yeah, our answer is going to probably be this 92 value, so we can round there. But I'm just going to say let C equal 92.15826. I'm going to check n of C, and we can go back to our calculator and call for evaluate n at time t equals C, and that's where I get 494.637 bugs. Oh, that is more, and that is actually kind of close. I didn't realize that. I had only looked at the graph and said, oh, okay, I know that because it's an interior critical point, it's the only maximum, it's got to be the absolute maximum. Okay, that's because it's the only interior critical point and it's a maximum, therefore it's an absolute maximum. I feel like I said that maybe possibly wrong. And because I've already defined that letter to mean that number, okay, I can just say max bugs happens at time t equals c. That's all the supporting work I need, all the justification. Okay, so that's all for this quiz. That took a long time, but I just wanted to make sure I showed all my steps. I know this was troublesome for y'all, so I wanted to provide the adequate support. So that's all for this video. Thanks for watching.